Welcome to this walkthrough for October 2020, Paper 1, OCR A-Level. Right, let's have a look at this, see what we've got. So obviously that's your front cover. We have our formula sheet, which is there. And then we have question 1. So it says, for a small angle theta, so there's some important things in there. We know that it's small, and we know that we are in radians. Show that 2 cos theta plus 1 minus tan theta all squared is approximately, that's always quite useful there, approximately equal to 3 minus 2 theta. Well, we glossed over the fact we had the formula sheet, but that's going to be really important to us. So formula sheet then, we can see on the formula sheet, small angle approximations. We've got that equivalent sign again, approximations, approximately, always useful to look for. We have sine, we have cos, we have tan. We're told it's in radians and it's small. So we go back, we note that we've got sine theta is theta, cos theta is 1 minus a half theta squared, and then tan theta is theta. So what have we got? 2 cos theta. So 2 cos theta plus 1 minus tan theta squared. Well, that's going to approximately be 1 minus, let's just double check what that was, a half theta squared, 1 minus a half theta squared plus 1 minus, and then I know tan theta is theta squared. So this is therefore 2 minus theta squared plus 1 minus 2 theta. Then you've got theta, minus theta times minus theta, which would be positive theta squared. So this is going to be 2 plus 1 is 3, minus theta squared plus theta squared, they cancel, and then you have minus 2 theta as required. Hence, okay, hence means we've got to use what we've just done somehow. Determine an approximate solution to 2 cos theta plus 1 minus tan theta all squared equals 28 sine theta. Well, for me, because it says hence, we're going to use those small angle approximations again. So we can say then that 2 cos theta plus 1 minus tan theta squared equals 28 sine theta. Well, we know the left can be written as 3 minus 2 theta. The right, or sine theta, is also theta, so that can be 28 theta. I can then start going through, solve that, so I've got 3 is equal to 30 theta, so theta is 3 over 30, or rather that theta is a tenth. That's good enough. It's small, so that will be a good enough solution for us. Right, let's move on to question 2. Simplify fully. Now, we could look at these. Some of these you might want to think, well, can I put these in the calculator? Not quite. We need to start doing some things with them first. So, what are we going to do? Well, this first one, I'm going to use some surd laws. So, we have root 12a times root 3a to the 5. Well, my surd laws mean I can break all these up. So I can have that. I can bring them in whatever order I want. So the 12 and the 3 can come together. So that can be 12 times 3. And then I can have a times a to the 5. So what have we got? 12 times 3, well, that's root 36 times root a to the 6. Root 36, nice and easy, that's just 6. I'm going to start using the power laws now, so the root is going to become power of half. So that is a to the 6 to the half. When I've got powers, I'm going to multiply those. 6 times a cubed, or just 6 a cubed. Question B. We have got 64 b cubed to the third times 4 b to the 4 to the minus a half. Right, what can we do? 64 to the third. I should know this, but I'm going to just check it on the calculator. So 64 to the power of a third. I was right, it is 4. So I can pop that in instead, because that power applies to everything in there. So that is 4. B cubed to the third is just b. Times, still with the negative, so I'm going to make it 1 over 4b to the 4 to the half. So then I'm going to have, let's put this all over the same thing. So I'm going to have 4b over, and then 4 to the half. 4 to the half, root 4, which is 2. B to the 4 to the half is b squared. And then that is going to be 4 over 2 is going to be a 2 on the top. B over b squared is going to be a b on the bottom. All right, let's move this down a little bit. So we have got, what's that gone? 7 times 9 to the power of 3c minus 4 times 27 to the power of 2c. 7 times 9 to the 3c minus 4 times 27 to the 2c. Now, first thing I do recognise is that both 9 and 27 are powers of 3. So let's deal with that first. So that's going to be 7 times, and then 9 is 3 squared to the power of 3c, minus 4 times 27 is 3 cubed. And then that's going to be 7 times, that's 3 to the 6c, minus 4 times 3 to the 6c again. So now we're in a position where we might have something that's pretty much just saying 7x take away 4x, because that 3 to the 6c is the same in both cases. So all we've got now is that we have 3 times 3 to the 6c. It did say simplify fully. So what we can do there is, because we've got 3 times this, it's actually 3, oops, it's not that at all. It is 3 to the power of 6c plus 1, because you're adding another power onto there from the multiply by 3. Right, question 3. Cylindrical metal tin of radius r centimeters is closed at both ends. It has a volume of, what's that, 16,000 pi centimeters cubed. It then says, show that its total surface area is given by 2 pi r squared plus 32,000 pi r to the minus 1. Oh, okay. So what have we got? Let's have a quick sketch of this. Right, what do we know? All we know is that we have a cylinder and that we have a radius looking like that. And we know that its volume is 16000 pi centimeters cubed. Not gonna lie, that's not very helpful to me at the moment. Oh wait, it's not too bad. We know the volume, we know there's a link between volume and radius. We could use that because we know that the volume of a cylinder is pi r squared h, area of the end multiplied by the height. Okay, so we know that 16000 pi is pi r squared h. So the pi's are going to cancel out, so 16000 is r squared h. Can't go very much more than that. I do want r squared in my answer, but I don't want any h's in this show that. So let's try and come up with an expression for the surface area. Now, surface area of a cylinder, you can imagine your tin of beans. You've got the paper wrapper, which is a rectangle. So we've got a rectangle where you've got the height, and that is the circumference, which is 2 pi r. You might use pi times diameter, you might be familiar with that, but we're going to use 2 pi r because we've got radii in the question. So, and then I've got 2 circles to go with that. So I'm going to have my surface area is going to be, what's that going to be? 2 pi r squared, because I've got the 2 circles, and that makes sense. 2 pi r squared. And then I'm going to have the area of that rectangle, which is going to be 2 pi r times h. So that's the surface area. I've got h appearing once in both of those, so if I make h the subject of that first expression we came up with, h is therefore 16000 over r squared. I can pop that into my expression on the right hand side, so this surface area is now 2 pi r squared. I'm going to leave that alone because I know that's in my answer, plus 2 pi r 16,000 over r squared. What are we going to have? So we know that 2 pi r squared is fine. 2 times 16,000 is 32,000 pi. Then I've got r over r squared. That is r to the minus 1, which is exactly what we wanted. So that is part A completed for us. Part B. Use calculus to determine the minimum total surface area. So told calculus, told minimum, so we know at a minimum dy by dx equals 0. Now, it's not going to be dy by dx in this because we don't have dy and dx in there. In this case then, for a minimum, we've got an expression linking a and r. So in this case, dA by dr is going to be 0. So if a is 2 pi r squared plus 32,000 pi r to the minus 1. Looks pretty awkward, but it's just some, if I'm differentiating that, it's just some really basic differentiation rules. So even if you haven't done the first part, you should be able to have a go at the second part. We've got 2 pi r squared, so I'm going to multiply by the power, so I'm going to have 4 pi r. Then I'm going to have minus, because I'm multiplying by the next power, 32,000 pi, and then I'm dropping that power by 1, giving me that. And then I therefore know that you get the minimum where this is equal to 0. So I can therefore say 4 pi r is equal to 32,000 pi, and I'm going to write this as r over r squared, just to make it a little bit more obvious about what's going on here. Just flicking between those power laws. If I multiply up by r squared and divide through by 4 pi, I'm going to get the r cubed, and let's just double check this. So I'm going to have 32,000, where's pi gone? Pi divided by 4 pi is 8,000. So therefore r is the cube root of that, cube root of that answer gives me that r is 20 centimetres. So we need to determine the total surface area, so we can work out the surface area in a minute. We need to justify that it is a minimum. So to justify that it's a minimum, the best way to do this is to differentiate that once more. So d2a by dr squared is going to be 4 pi. That's going to be plus 64,000 pi r to the minus 3. When I put 20 into that, so if r is 20, pi plus, let's just do the calculation, 4 pi plus 64,000 pi times 20 to the power of minus 3 is 12 pi, so that's 64. Gives me 12 pi, and we know 12 pi is greater than 0. Therefore, minimum. So the last thing we want to do is therefore find your minimum surface area. Therefore, minimum SA is going to be 2 pi times 20 squared plus 32,000 pi 20 to the minus 1. Again, this is just some calculator work. 2 pi times 20 squared plus 32,000 pi times 20 to the power of minus 1 gives me a minimum surface area of 2,400 pi centimetre squared. Right, that's question 3. Question 4. Question 4 looks something like this. Prove by contradiction there is no greatest multiple of 5. I'm not a big fan of proof by contradiction. Let's see if we can remember the steps. So, as always, we need to state what we're trying to do. So, we are going to assume there is a greatest multiple of 5. And we are going to call that 5k. Then I'm going to do 5k plus 5 is equal to 5 lots of k plus 1. Now, what can we say about this? Well, we know this is also a multiple of 5, as it has a factor of 5, and it is bigger than 5k, again because k plus 1 is bigger than k. Now this is the important statement that you need to have in your answer. This is a contradiction And then you want to, just to finish this off, this proves that there is no greatest multiple of 5. For 3 marks, that's probably going to get you everything that you need. Right, question 5. Ooh, vectors. I like a good vector. So, what have we got? The diagram shows points A and B which have position vectors with A and B and respect to origin O. P is the point on OB, such that OP to PB is 3, 1, and Q is the midpoint of A. So, P is in the 3, 1. So P is 3/4 of the way up. So P is somewhere about there on the diagram. Q is somewhere about there. Okay, let's have a look at what's going on there. Find P to Q. So P to Q, I need to go from P to O. And then I need to go from O to Q. That's the easy part. Now we've got to work out what some of these are. P to O. Well, we know that's 3/4 of the way backwards along B to O. So that is 3/4 of the way along B to O. And then O to Q is halfway along L. Oh no, it's not. Q is the midpoint of A to B. Oh, I've got Q in the wrong place. So let's find A to B. A to B is this line, and Q is that line. So we've gone along there. So O to Q is a little bit tricky. We need to go, let's lose this half. Don't want that just yet. We need to go O to A, and then we need to go half of A to B. A to B we haven't touched on yet. Let's do this on the side. A to B is go backwards along B to O, and then forwards along O to A. So that's going to be minus B plus A. Right, so we've got 3/4 of B to O. B to O is negative B, so that's negative 3/4 of B plus O to A, which is A, plus a half of A to B, which we worked out on the right, which is A minus B. Oh, we could tidy some of this up. So I've got A plus a half of A. That's going to be 3/2A. Then I've got negative 3/4 B, negative half B. Let's just check what that is because I don't want to make mistakes on my fractions. So I've got negative 3/4, and then I've got negative half. So that's minus 5/4 of B. Does that make sense? To go from that red dot at P to the red dot of Q, I've got to go, well, A is going right, and I do have to go sort of in a southwesterly direction to get back from a right-hand direction. Yeah, okay, that's fine. The line OA is extended to a point R, so that PQR is a straight line. So let's do that. Let's have this line extends out here, and then we're going to have it so we have this straight line, which is PQR. which is going to be down there, so that means that R is somewhere along there. Explain why PR is k lots of 2a minus b, where k is a constant. Why is it that? Good question. Let's find well, if it's a straight line, and that makes me wonder if I've made a mistake. Makes me wonder if I've made a mistake here. Let's go back and just double check part A. 3 over 2a. So we have got P to O, that's minus 3/4 of B. Oh, I have made a mistake. My AB is not correct. I have made a mistake, and we'll talk about how I spotted this mistake in a minute. So AB should have been backwards along A, so that was negative A plus B, because I should have done, I should have gone AO plus OB. So that means that's going to change that in the brackets. So that is going to be B minus A. So then I'm going to have minus 3/4 of B plus a half of B. So let's just double check this on the calculator because I don't want to make any more mistakes. So I've got plus a half there. So that's minus 1/4. It feels like that's going to be more like what I'm looking for. And then I've got 1A take away a half of A, which is going to be a half of A minus 1/4 B. So I've been back and I've fixed that. And then the reason I've spotted that is because explain why this PR is k lots of 2A minus B. So what I was thinking was P to Q and Q to R are collinear. Now, those of you who remember doing GCSE vectors questions will remember collinear vectors cropped up all the time on there. You had to prove things were collinear, and you did that by proving that two things, that the lines were parallel and they went through the same point. Well, the same things apply here. These lines have to be parallel if it's a straight line. If they are parallel, the two vectors have to be multiples of each other. So what I noticed when I looked at my answer and the answer in the question was that my vectors weren't, one of them wasn't double what I was getting for the other component. So that made me think, well, have I done my question wrong? I need to go back and check that. And you can see that I've done that there. So explain why P to R has to be this. P to R equals k lots of 2A minus B, because PQR is a straight line, and then this means that P to Q and Q to R are co-linear. So that means that PQ and QR are parallel and they pass through the same point, but that's not relevant here. The same point. So if they are parallel, their directions or their gradients, if you will, their directions must be multiples of each other, and then PQ, so P to Q is, what do I need to take out as a factor? If I were to take out a quarter, I would get 2A minus B. So therefore, you've got to be some other multiple PR must be some other multiple of 2A minus B. As required. That's probably a bit of an overkill for what this question actually wants, but that's what's happening. So it then asks us to hence determine the ratio O to A to AR. Right, what are we going to do on that one? So what are we going to do? So we could do, let's look back at our diagram. We need to get from A to R. Well, I might be able to say something along the lines of AR is AQ plus QR. Is that going to go anywhere? Because we know what OA is. OA is going to be, that's just A. So OA is that. AR, oh, I know how we're going to do this. AQ we've already got somewhere. AQ is half of AB. So A to Q is half of B minus A. And Q to R is K lots of that 2A minus B. Because it's just another multiple going in that direction of 2A minus B. Because if PR is going in that direction, PQ is going in that direction, QR has to as well, because they're all going in a straight line. So we can start expanding these brackets. So I've got half B minus KB. So I've got half minus KB, and then I've got minus a half A plus 2KA. So I've got plus 2K minus half A. Now, the bit that I hadn't thought about initially, but now I spotted, A and R are in a straight line, both heading in the direction of A. So what that means, because it's horizontal and horizontal only, there are no components of B. So that means the B component in AR is 0. So this highlighted component here has to be 0. It has to be 0 so that the AR points in the correct horizontal direction. So therefore, half minus K is 0, because we're not actually interested in the B's, we're only looking at coefficients here. Half minus K is 0, so K is a half. So what that therefore means, AR is 2 lots of a half minus a half lots of A, so that's 1 minus a half, so that's a half A. So therefore, we can look at this ratio we were asked for, which double check is OA to AR. So therefore, OA to AR, well, that's A to a half A. If we cancel the A's out, I just get 1 to a half, or 2 to 1. Right, that was quite nice. Question 6. Question 6. A mobile phone company records their annual sales on the 31st of December. Paul thinks that the annual sales can be modelled by the equation S equals AB to the T, where A and B are both positive constants and T is the number of years since the 31st of December 2015. Paul tests his theory by using the annual sales figures from 31st December to 31st of December 2019. He plots these on a graph with T on the horizontal axis and log 10S on the vertical. Explain why, if Paul's model is correct, the results should lie on a straight line of best fit on his graph. Okay, so let's have a play about with this. The explain why, it's not really asking for it wordy. They're basically saying, can you take that equation you were given and turn it into a straight line? So let's try and do that. I don't really want that first sentence. I do want that though. So we have got S equals A, B to the T. What information have we got? We've got T on the horizontal axis. So T's on the horizontal axis and log 10 on the vertical. So let's take log 10s. So log 10S is log 10 of A, B to the T. We then need to split the right hand side up with our log laws. So log 10 is log 10 of A plus log 10 of B to the T, and one last step. Log 10S is log 10A plus T log 10B. And what we've got there is, if we compare that with y equals mx plus c, it is the wrong way around to the way you would normally write it. But you can see, if you plot that graph, so by plotting the graph in the question, it should produce a straight line with a gradient of log 10b. That's me. Of log 10b and and y-intercept of log 10a. And I think that's how I would explain. The results line a straight line of best fit, which has a gradient of 0.146 and an intercept on the vertical axis of 0.583. So use these values to obtain estimates for A and B correct to two significant figures. So let's do that then. So part B, we are told M is 0.146 and we're told C is 0.583. So we've just said there the gradient is log 10 of B. So let's do that then. So log 10 of B is 0.146. So we anti-log it. So if you have the button log on your calculator, which is over here, you can anti-log that by doing shift. You could just do 10 to the power of, but you can do shift log, and you'll get that 10 to the power of. And all I'm going to do is put 0.146 in there. So B is 10 to the power of 0.146. And what was the accuracy? Two significant figures. So B is 1.4. Use these values to obtain estimates for A and B. So we have got C is 0.583, and we just said the y-intercept was log 10 of A. So log 10 of A is 0.583. So again, exactly the same, 0.583. I'm going to anti-log that. So I've got shift 10 to the power of 0.583. Gives me then it's 3.8 to two significant figures. Is 3.8. So it would be a good idea, looking at what we're going to have next. Use this model to predict the year in which, on the 31st of December, the annual sales will first be recorded as greater than 200 million. So we have got, we're going to go back and do our original model of this, which was S equals AB to the T. Let's just double check what everything was. S was the annual sales. So let's pop in what we've got. So S equals 3.8 times 1.4 to the T. And let's just double check this. So that is the number of millions. So that is the number of millions in each of those. So we want to make this greater than 200 rather than 200 million, because if we go back, we can look at that initial piece of text. It's the annual sales. Whoops, wrong pen. It's the annual sales S million. So people get caught out by that every single time. I've been caught out when doing this paper in the past, or on similar questions. So when I'm making my inequality, because it's, when we're talking about greater than, that's clearly what we're going to do in inequality. We're only making our inequality greater than 200 rather than 200 million. So let's say our sales will be greater than 200 million. So I'm going to say 3.8 times 1.4 to the T is greater than 200. So I'm going to have 1.4 to the T is greater than 200 over 3.8. I'm going to deal with that number in a minute. I'm going to take logs of this because I want that power to come down. You can take whatever base you want. I'm going to take ln because it's very slightly fewer button presses. So ln of 1.4 to the t is greater than ln of 200 over 3.8. Again, I'm going to just leave it like that. The calculator can do the heavy lifting for me. That t is going to come out the front. And then I want to divide through by ln of 1.4. So t is greater than ln Now, it's always a good idea to double check that none of these numbers you're dealing with are actually negative, and then I'm going to flip the sign over. So let's just have a look at that. ln of 1.4. No, that's positive. And then ln of 200 divided by 3.8. That's also positive. So if we just do the calculation, we get that t is greater than 11.77 years. So t is 12. So let's double check the question. Which year on the 31st of December the annual sales would first be greater than 200 million? So what year did we start? This is years since 2015. So I want to do 2015 plus 12. 2015 plus 12. Really should be able to do that in my head. That was 2027. So therefore, this is December 31st, 2027. Now, part D, the usual question when we're looking at any kind of modelling. Give a reason why this prediction may not be reliable. Well, with the benefit of hindsight, and to be fair, when this paper came out, you could probably have used this example. The paper came out in 2020. That was the year of the global pandemic. In 2015, when this model was when they came up with it, they were not planning for a global pandemic, and we all know what happened in the pandemic. Lots of people lost their jobs. The economies tanked and became quite difficult money-wise for lots of people. Businesses included. Lots of businesses didn't make it out of the pandemic. So this is the kind of thing you can put in there. Something like natural, unpredictable natural disasters will get in the way of the model, meaning it won't follow consistent patterns. Anything where you're talking about the fact that this is a model, but it probably won't last forever, is a good sort of answer to that question. Right, let's have a look. So we need to move on to question 7. Two students, A and B, are starting a revision program. They will both revise for 30 minutes on day 1. Anna will increase her revision time by 15 minutes every day. So she's doing an arithmetic progression because she's doing the same amount every time. Ben will increase his revision by 10% every subsequent day. So he's doing a geometric progression. Verify that on day 10, Anna does 94 minutes more revision than Ben, correct to the nearest minute. So let's have a look. We identified that A, she was 50 minutes extra every day. She's your arithmetic. And in your arithmetic, you need a first term, which is A, and we know that is 30. And you need a constant difference, D, which we said was 15. Person B, we said was a geometric because you're doing a percentage increase every day. And again, you need a starting value, which again is 30, and this time you need your common ratio. So what are they going to do? An increase by 10%. Well, that is a common ratio of 1.1. Verify that on day 10, Anna does 94 minutes more revision than Ben, correct to the nearest minute. So day 10, we're not looking for a sum of it, we're just looking for the value of each of these on a particular day. So we need U10, and for the arithmetic, that is A plus n minus 1 D. Not given to you on the formula sheet, you do have to know that. So that is 30 plus 10 minus 1 times 15. So we just stick that in the calculator. 30 plus 10 minus 1 times 15. Need to put times in there. Is 165. The geometric then, U10 for the geometric, is A r to the power of n minus 1. So that is 30 times 1.1 to the 10 minus 1. So that is 30 times 1.1 to the power of, I'm just going to do 9, I can do 10 take 1 in my head. So that is 70.7. 70.74, which is about 71. So that's about 71. So then we're going to just 94 minutes. So we're going to do A take B is 165, take away 71, which to absolutely nobody's surprise, 165 take away 71 is about 94. And it's a verify, we just need to show that that's the case. Let day X be the first day on which Ben does more revision than Anna. Show that X satisfies the inequality log of 1.1 0.5x plus 0.5 plus 1. Right, this is a show that with no real clues as to how we got there. Log of base 1.1. Log of base 1.1 probably means we're going to be doing something to get that power down. So let's look at the amount of time that each does on this respective day X. So for my arithmetic, what have we got? We have got, so this is U of day X. That is going to be, not sure whether we use 0.5. We'll go with it. We'll see what happens. I'm going to use 30, even though they've said, they have talked about 30 minutes, so I'm going to go with it so far. I'm wondering if that 0.5 is half an hour. Let's see. So UX is 30 plus X minus 1 times 15. And for point B, UX is 30 times 1.1 to the power of X minus 1. Now we know Ben does more revision than Anna, so that means that 30 times 1.1 power of x minus 1 is greater than 30 plus x minus 1 times 15. So, I see where it comes from now. If I divide through by 30, I'm going to get 1.1 times x to the minus 1 divided by 1 plus a half lots of x minus 1. Just put that 15 to the front, and then I can expand that bracket, and I'm going to get pretty much what's on the right hand side. So I'm going to get 1.1 to the power of x minus 1 is greater than 1 plus a half x minus a half. So 1.1 to the power of x minus 1 is greater than half x, or 0.5 if you will, plus a half. And then I'm going to take logs of base 1.1. So that is going to mean that I have x minus 1 is greater than log of 1.1 of a half x. Let's go with 0.5 like it asked for in the question. So I'm going to have 0.5 plus 0.5, which gives that x is greater than log of 1.1 0.5x plus 0.5 plus 1. And I think that is what we were asked to do. See that just at the top of the screen. So we then have to use the iterative formula. I'll copy this down so I can actually see it. So my iterative formula is xn plus 1 is log 1.1 0.5 x to the n, or xn, sorry, plus 0.5 plus 1, and we are told x1. You should show the result. x1 is 10, and we're trying to find the value of x. It doesn't actually give us a goal, an accuracy level, so let's see what happens. So let's have a look. We know that x1 is 10. So let's load this up into the calculator. So I'm going to go 10, hit equals, and then we're going to have log of base 1.1. I got 0.5 times the answer. Wherever you have an xn, you put answer plus 0.5. We go outside of the log. Whoops, back to the end. Plus 1. My second iteration is 18.88. I guess as we're after a whole number of days, we just want to find a value that this settles at pretty consistently. So 18.886. And as it's days, we do want an integer. Yeah, you can see we want a couple of these where it settles down. So 25.099, 27.951, 29.03040, 29.426. It looks like the answer. Let's just do a couple more just to check it's not going to go wildly off. X to the 8 is 29.607. So, therefore, if we're saying that if we're going to get closer, and I'm not going to do write any more down, but we can just see, yeah, the iteration is getting much closer. We're just affecting those last few decimal places now. So it's 29.6 is the day. So that means that X, this is the first day that he does more revision, is day 30. All right, let's go back and read this question. Give a reason why Anna's revision program may not be realistic. What was Anna's? Anna will increase her revision time by 15 minutes for every subsequent day. Let's talk about the fact, just having read ahead to the next question as well. So, Anna's may not be realistic. It is unrealistic to ensure that you increase revision every day. Illness may prevent this for example. And then you want to find another reason that is not the first one, that's not the same reason, but you want to do another reason. It doesn't matter that it's the other person. Let's just have a look. How long is he revising for on day 30? So we said initially it was 30 times 1.1 to the power. This will be 30, take away 1. 475 minutes, which happens to be, that's not helpful to me, that's about 8 hours a day. And then if we increase that by 1.1 again, 8 hours, 9 hours, very rapidly. We're going to say very rapidly. They will be revising for more hours than there are in a day. And let's be honest, I want my students to revise, and I don't want them to revise for 12 hours a day. I actually want them to be normal human beings as well. Question 8. Lovely, lovely differentiation. Differentiate 2 plus 3x squared, all multiplied by e to the 2x with respect to x. The fact that I said multiplied by tells me I'm going to use the product rule. So, we have got, let's say, y equals 2 plus 3x squared e to the 2x. Product rule, u is 2 plus 3x squared. V is e to the 2x. What have we got? Differentiate those. du by dx is, the 2 just disappears, so that's going to be plus 6x. The v is going to become dv by dx, and that is going to be 2e to the 2x. You're not given the product rule on the formula sheet. That'll be the quotient rule you get. Luckily, the product rule is dead simple. You just u dv dx plus v du dx. It doesn't matter which way around you do it. So, therefore, dy by dx is u dv dx plus v du dx. So that is 2 lots of 2 plus 3x squared e to the 2x plus 6x e to the 2x. And because I don't want to make my job any harder than it needs to be, I'm not even going to bother looking to see if it does tidy up at all. I'm just going to leave it in that form. I don't want to spend time doing things I don't need to do. Hence show that 2 plus 3x squared e to the 2x is increasing for all values of x. So the way we're going to do this is we are going to, it's almost going to be like proof by induction if you've done further maths. Almost. So what I'm going to do is I'm going to say, well, it is going to be increasing at a particular value, and I'm going to show that it has no turning points. So therefore, if it's increasing at one value and does not change to be decreasing at any point, it must therefore be increasing for all values of x, which is very loosely like proof by induction, but that's not the focus. So let's find a really easy place. So when x equals 0, dy by dx is 2 lots of 2 plus 3 times 0 squared e to the 0 plus, well, that's just going to be 0. What else we got? So we got 2 lots of, well, 3 times 0 squared is that. So that's just 4. dy by dx is just 4. You can double check that on the calculator if you want. So therefore, function is increasing at x equals 0. I then wanted to show, what does it want to do? Show that it never has a turning point. So if turning point, so turning point, or it's a stationary point, and you should know that dy by dx is 0. So therefore we can say 2 lots of 2 plus 3x squared e to the 2x plus 6x e to the 2x is equal to 0. Now here I am going to start thinking about factorising it out. Common mistake would be to divide through by e to the 2x. Don't do that, you lose some solutions, although they're not helpful to us. So I've got e to the 2x that I can factorise out. So then I'm going to have 4 plus 6x squared. 4 plus 6x squared plus 6x is equal to 0. We know e to the 2x is never 0. Because by definition, if you look at the graph of e to the 2x, comes along, never hits the axis, and then just does that. So it's asymptotic to the x-axis, never hits it. So we can then have a look at this. What's turned out to be a quadratic, so therefore 6x squared plus 6x plus 4 is equal to 0. I want to show that it doesn't equal to 0, so I'm not going to sit there and do any solutions. If it's increasing, we're trying to show that it doesn't turn around, so I think the best bet to do here would be to find the discriminant. What you might have been tempted to do is get your quadratic solver and show that you get imaginary answers from it, but realistically, if you've seen that, you should then be proving what or showing why that happens, and that's because the discriminant is what's it going to be? Discriminant is going to be negative. So let's have a look. So b squared minus 4ac is equal to 6 squared minus 4 times 6 times 4. So let's get the calculator to do the heavy lifting again. So we've got 6 squared minus 4 times 6 times 4. Oh, look, that's negative 60. So therefore, that means 6x squared plus 6x plus 4 equals 0 has no real solutions. So therefore, the curve has no turning points where dy by dx is 0. So as it is increasing when x is 0 and never turns. The curve must be increasing for all values of x. Okay, right, what are we on to now? Question 8. I think it's question 8. No, question 9. That looks like a modulus graph. I haven't even read anything yet. What's this? Question 9. Diagram shows a graph of y equals mod 2x minus 3. I was right. State the coordinates of the points of intersection with the axes. So let's do this in that top space so I can keep the graph and the text together. So let's deal first with y equals 2x minus 3. Well, it's going to hit the x-axis, that circle part, when y equals 0. So 0 is 2x minus 3. So I have got 3 over 2 there. Let's mark that on. I'm going to mark it on the graph. It's probably going to be useful to me. And then we know anything that goes below the axis is going to be bounced back up because it's a modulus. So that means if the intercept of y equals 2 minus 3 would be minus 3, that means it's going to be positive 3 when it bounces back up. So that is 3. So that means my intersections, let's write those on now. My intersections are 3 over 2, 0, and 0, 3. Given the graphs of y equals 2x minus 3 and y equals ax plus 2 have 2 distinct points of intersection, determine the set of possible values of a. Right, this is going to be one of those ones where the horrible mark scheme just says something like writes down a particular value, and you look at it and you go, I have no idea why. And me too. So let's have a look at why that is. So y equals ax plus 2. So that means we are going to go through 2. So 2 is going to be somewhere about here on my axis. And then it has 2 points of intersection. So that means I have a line that could come anywhere pretty much down like that. So that means if it goes through that intersection there, at the bottom, that's going to be one limit. So let's have a look at that. So we're trying to find a gradient. So what's that? It's going to be a negative gradient. So let's find the gradient between 0, 2 and 3/2, 0. Because I think that's going to be our lower limit. Might be an upper limit, who knows. So m is y2 minus y1 over x2 minus x1. Y2 minus y1 is going to be 0 minus 2 over 3/2 minus 0. Let's just double check that. So 0, oops, 0, no, I need fraction first. 0 minus 2 over 1.5 take 0. That's minus 4/3. Okay, so that's going to be probably our lower limit. Let's see what the other versions are. Then what else are we going to have? Go back to our diagram. Let's get rid of this line again. So 2 is there, 3 is there. If we have a positive gradient that is, if it is 2, which is the gradient of the original line, it's going to come along, it's going to do that. These two lines there are going to be parallel, so we're going to have the intersection there only. So 2 seems to be an upper limit there, because if I go any steeper than that, like that for example, that is just going to continue moving away, so we'll have the one intersection. So it looks like we have 2 as an upper limit. And I suspect that's the one that it just says the upper limit is 2. So we then, anything where it's not 2 is going to keep giving us these lines that are going to intercept twice until we get down to that minus 4/3. Then after we go past minus 4/3, if we get rid of those lines, after we've had that, and then we go steeper, we are going to intercept, let's do a few more. We're just going to intercept the line when it bounces back behind. So we have our 2 values. So the possible values of A then so A is, it can be equal to negative 4/3, that would be fine, but it has to be less than 2, because if it is 2, it's going to be parallel, it's not going to intercept. So the x-coordinate, the points of intersections of these graphs, giving your answers in terms of A. So that looks like we're solving these simultaneously. So let's have a look at some space. So it says we want to have do mod of 2x minus 3 is equal to ax plus 2. So you're going to do these in two different ways. First off is you're just going to say 2x minus 3 is ax plus 2. So you're going to have 2 minus a x is equal to 5. So x is 5 over 2 minus a. That's the first one. And then, because it's a modulus, you're going to do it again, but with a negative version. So you're going to have 2x minus 3 is minus ax minus 2. Make either side negative, whichever one is easier for you. So again, 2 plus a x is equal to minus 2 plus 3 is 1. So x is 1 over 2 plus a, and I think that's it. Right, how are we doing? Question 10. What's this? Numerical integration. So the diagram shows the curves y equals sine of a half x root x minus 1 for between 1 and 2. Use rectangles of width 0.25 to find upper and lower bounds for this. Give your answers correct to 3 significant figures. Right, rectangles. So what's going on here is we've got two situations. So we want 4 rectangles because we've got width of a quarter, and essentially we're going to split this. So if we look at the diagram, split that into 4 trapeziums almost, which is what you're probably more familiar with doing. But if you wouldn't do rectangles, instead of doing dot to dot, you can find rectangles, and I am doing an example of the lower bound here. So I've made my rectangles like that. So I want to find my x values at the bottom end of the thing. So I'm going to have, I want to do 0.25 because that's going to be the height, and then I'm going to have my 4 different heights. So I'm going to have, in this case, I'm going to have a height there, a height there, a height there, and a height there. I'm actually going to use table mode to help me do this. So, oh, I've got the wrong calculator on. I've got the GCSE calculator on. It's okay, I can do table mode with the GCSE calculator. So f of x is, I want sine of a half square root, and I want, where's x gone on this calculator? X minus 1, and I'm going to close some brackets, and I don't want a g of x. I want the table to start at 1, I want it to end at 2, and I want it to go up in steps of 0.25. So I'm going to look like that. So I'm going to use my heights then this way around. So I am going to have, I just want the first 4. I don't want the last one because I want these ones at the left hand side. So I've got, whoops, that's blue, I want red. That's 0 plus 0.2474 plus 0.3462 plus 0.4196. I'm going to calculate that in a minute. I'm going to do the upper bound calculation first. So I've got the numbers to hand. So my upper bound then is going to be a similar sort of thing, but instead, when I draw my rectangles in, so I've got half, half, and half, instead of doing everything on the left hand side, I'm going to now, my rectangles looking like that. So you can see I've got a slight over approximation. So I'm now going to use the values from the right hand side of the rectangle. So that would be values 2, 3, 4 and 5 in my table. So that would be 0.25 lots of 0.2474 plus 0.3462 plus 0.4196 plus 0.4794. Now I've got those written down, I'm going to go back and just do the calculations. So 0.25 0 plus 0.2474 plus 0.3462 plus 0.4196. So my upper bound, I don't want to give it as a fraction because that would imply it was an exact answer, is 0.2533. My upper bound, I'm just going to use the replay function because I don't want to type all that in again. You could just leave 0 in. I'm going to adapt it to make it my last one, 0.4794. All the rest of it's the same. And in this case, my upper bound is 0.37315. Give your answers correct to 3 significant figures, so that means I'm going to have 0.253 and 0.373. Use the substitution to show that. So we're going integration by substitution now. So as ever, we are told the substitution. So we have got that t is root x minus 1. So I want to find dt by dx. I'm actually going to make another substitution. I'm not very good at doing integration by inspection. So I'm going to say, well, I'm going to u equal x minus 1. So du by dx is 1. So du is going to equal dx. And what can I do there? I can say then that t is root u Wait, no, I've done the wrong rule. I've done the wrong rule. I want to differentiate this, don't I? So t is x minus... No, I was doing it right. So t is u to the half. Don't need that du by du equals dx. So dt by du is going to be a half u to the minus a half because we're doing the chain rule here. So there, what do I want? I want dt by dx, and that's going to be dt by du times du by dx, which is just going to be a half u to the minus half, and u is x minus 1, so a half x minus 1 to minus a half. Okay. So let's write this in a different way, just so I can see what's going on. I've confused myself a little bit. So let's tidy this up a little bit. dt by dx is 1 over 2 root x minus 1. Okay, so we're going to go back and we're doing the integral of sine a half x minus 1 dx. I want to get dx in terms of dt. So from that bottom thing we've just done, let's do that. So we can say then that 2 root x minus 1 dt is dx. And if you remember, we were given the substitution that root x minus 1 is t, so 2t dt is dx, because if we compare those two statements, we can make that substitution down in there. So now we've just got a case of substituting everything back in. So this is the integral of sine of a half t, then dx is 2t dt, which is exactly what we wanted. So that is the integral. I'm going to bring the 2 out the front because I like my 2's at the front. So that is t sine a half t dt. And it then does hence show that the integral is equal to that. So let's do that integral. So we're doing the integral of sine half x minus 1 dx, and that is 2t sine half t dt. Limits we had on this were 2 and 1, unsurprisingly. And then to me, we've got to recognise what rule that is. To me, that looks like that's going to be the integration by parts, because integration by parts is pretty much the product rule for integration. So let's go back and write down integration by parts so we don't get that wrong. Let's find it on our formula sheet. So right back to our formula sheet, integration by parts, just above the small angle approximations we used earlier. So we have got the integral of u dv dx is equal to uv minus the integral of v du dx dx. Okay, got that, found that. Let's go back to our question. Okay, so what do we want? Well, we want to find one of our functions is going to get integrated and one of our functions is going to get differentiated. So we either have t or we have sine of a half t. We want the one that we differentiate to become easier, and t becomes easier. That's the one you always pick unless you've got an ln in there. So t is going to be u, and then dv by dx is going to be a sine of a half t. We know we want to differentiate u, so du by dt is 1. We want to integrate sine, so sine, which way around does it go? Sine cos minus sine minus cos, so sine's going to go back up to minus cos, and then it's going to be 1 over, so that's going to be 2 minus 2 cos of a half t. It's going to put all this back. In fact, I'm going to bring that 2 back inside my integral sign. It's just going to make things a little tidier. So that's a 2t, and then that's going to be just 2. That's going to be 2. So let's go and use our formula. So this is uv. So that is minus 4t cos a half t minus the integral of 2 sine of a half t minus 4t cos of a half t, and that was dt. What do we got? So we need to integrate sine again. So sine, we already said, goes to minus cos. So that's going to be minus 4 cos half t. But I've already got a minus. That's going to be positive 4 cos half t. I'm not going to put plus c because we've obviously got brackets. No, we don't. We have a definite integral. So we are now just going to go through, and we're going to do this with 2. We're going to do this with 1. We can make sure we're in radians, which we are. So I've got minus 4 times 2. Do I want this in exact form? What am I looking for? I do want this in exact form. Oh, I haven't changed my limits, that's why. Have I made a mistake in here? UV, yeah. V du, well there's a mistake in there already. So V du, that's going to be I've made a huge mistake. Again, my show that's telling me this. So what have I got? UV is 2t minus 2 cos half t. That is fine. That's minus 4t cos half t. And then I've got the integral of v du. So that is minus 2 times 2 cos. There's where the sine is going to come from. So that's positive 4 cos of a half t. My limits are going to be different. So this is going to be integral of 4 cos half t. So that's going to be, cos goes to sine, so that's going to be plus 8 sine half t. Easy peasy then. So let's go with, so new limits, if x equals 2, t equals 2 minus 1 is 1 rooted, t is 1. If x is 1, t is 0. That's nice. So we are going to have minus 4 cos of a half. So cos of a half, why am I blanking on cos of a half? Let's just double check that. Cos of, yeah, cos of a half. Minus 4 cos of a half. That's not very nice. Cos of a half, root 3 over 2. So that's minus 4 root 3 over 2 plus 4, because sine of a half is a half. Take away when t is 0, that first term is 0, 8 sine of 0. Sine of 0 is 0. That's not what we were looking for. Ooh, they haven't worked these things out. They haven't worked these things out. Oh, let's try doing that then. Odd way of doing it. So x is 2, so we're going to get t is 1. So I've got minus 4 cos a half plus 8 sine a half minus, oh, that's all 0. I better do it because it's to show that. Minus 4, lots of 0, cos of 0, plus 8 sine of 0. That will go to 0. That will go to 0, which gives me, hopefully, 8 sine a half minus 4 cos a half. Right, and we are rapidly getting towards the end. I want to try and get that done pretty quick. Right, question 11. Must show detailed reasoning. In the diagram, the circle meets the equation with x squared plus y squared minus 10x minus 14y plus 64 equals 0. Tangent is drawn. Right. What do we know about this? Not very much. Let me find out some information about this circle. Right, let's find the centre and let's find the radius. It's going to be helpful here. So we've got x minus 5 plus y minus 7 all squared minus 25 minus 49 plus 64 is 0. X minus 5 all squared plus y minus 7 all squared. What have I got? 25 plus 49. And then take 64. Gives me 10. Okay, so we know this has a centre of 5 and 7. And we know that it has a radius of root 10. Create this tangent of form y equals mx plus 2, where m is a constant greater than 1. So at this point, so the x-coordinate of A is where both of those things are true at the same time. So what can we do here? Simultaneous equation. So we have got what have we got? So we've got x squared plus the y squared is mx plus 2 minus 10 lots of x, so happy with that, minus 14 lots of mx plus 2 plus 64 is 0. X squared plus m squared x squared plus 4mx, yeah, that's right, plus 4 minus 10x minus 14mx minus 28 plus 64 is 0. Let's tidy this up a bit. So I've got m squared plus 1 x squared. I've got 4m minus 14, so that is 10 minus 10m minus 10x, and then I've got 4 plus 64 is 68, take 28 is 40, that's good. So then just a little bit of tidying up to get it in the form that they want. They want me to take a factor of minus 10 out of there, so I'm going to get m plus 1 x plus 40. Right, hence determine the equation of the tangent to the circle at A, which passes through P. So, that's my x-coordinate. If it's a tangent, that means it only intersects once, so that means the discriminant is equal to 0. So let's go with that. So b squared minus 4ac is equal to 0. So b squared, that's minus 10 m plus 1 all squared minus 4 times m squared plus 1 times 40 is equal to 0. So I've got 100, and then I'm going to square out this bracket on the inside, so that's going to be m squared plus 2m plus 1 minus 4 40s are 160, so that's minus 160 m squared minus 160 is equal to 0, so that's 100 m squared plus 200 m plus 100 minus 160 m squared minus 160 equals 0. What can I see in there? Instantly I can see I can divide through even before I've gotten to tidying up by 10. So 10 m squared, let's do it all as one rather than confusing the issue. 100 minus 160, that's minus 60 m squared. 200 m is the only one of those, so plus 200 m, and 100 take away 160 is again minus 60. That's equal to 0. It's not going to divide by 60, we're not that lucky, but it will divide through by 10, so minus 6 m squared plus 20 m minus 6 is 0, and it will divide through by 2, so minus 3 m squared plus 10 m minus 3 is 0. Let's flip all some signs around just because it's going to make things a smidge easier for myself. So I'm going to have 3m squared minus 10m plus 3 is 0. We're going to the old AC method, so I want two numbers that multiply to make positive 9 and add up to be negative 10, so that's minus 9 and 1. So I'm going to have 3m squared minus 9 m minus 10, nope, minus 1m plus 3, I can get rid of that erroneous bracket, equals 0. Factorise out the first two, so that is 3m m minus 3. I can take a factor of minus 1. So I get then that the 3m minus 1 and m minus 3 is 0. So those are the two gradients of lines that are tangents. So therefore m equals 3 or m equals a third. But the equation of the tangent is in the form y equals mx plus 2, where m is a constant greater than 1. So we know m is greater than 1, so m equals 3. So my tangent is y equals 3x, let's double check it, 3x plus 2. And I think we're on the last question. we are just what I need. A nice differential equation to finish off. Right, find the general solution of the differential equation. Give your answer in the form y equals f of x. So we're going to do this by separation of variables, because it's the only thing you can do in A-level maths to solve a differential equation. So it means I'm going to get everything with a y onto the left-hand side and everything without a y onto the other side. It means I'm going to have 1 over y dy, and integrate that, is equal to 20x minus 35 over 2x cubed minus 3x squared minus 11x plus 6 integral dx. Now, left-hand side is dead easy. We can deal with that. The right-hand side's not great. I probably should have found a more appropriate method. So I want that version of the calculator, and I want to double check what's going on in the denominator of this, because I think I'm going to go partial fractions, and I'm going to check this by solving it. So my polynomial, it's a degree 3. It is 2, it's minus 3, it's minus 11, and it's 6. And there we go. So this can be written as 1 over y dy is the integral of 20x minus 35, sorry, over, and then that's going to be x plus 2. I'm going to have x minus 3. And I'm going to have 2x what's that going to be, minus 1. Let's just double check all those. Plus 2, minus 3. Yep. Right. So that's just from experience that we haven't really seen partial fractions yet. So it's going to be in here somewhere, and I do like it in a differential equations question. So we can then start to look at the partial fractions bit, and we can say something along the lines of 20x minus 35 over x plus 2, x minus 3, 2x minus 1 is equal to a over x plus 2 plus b over x minus 3 plus c over 2x minus 1. Usual method for this, 20x minus 35 is a x minus 3, 2x minus 1 plus b. I'm going to run out of space on this, but I'm going to do it anyway. Plus b, and that's going to be x plus 2, 2x minus 1, and this is where I'm going to lose space, c, and that's going to be x plus 2, x minus 3. Can I move that across slightly? Yes, I can. And then I'm going to pick some values. So if x is 3, that means that I'm going to get, so let's pop back into normal mode, 20 times 3, take 35. I'm going to get that 25. If I want x is equal to 3, well, that means that x minus 3 as a bracket in the first one and x minus 3 as a bracket in the last one disappear. So I'm just going to get brackets that are going to be 3 plus 2, 2 times 3, take 1. That's going to give me 25b. That's nice. I'm going to say then if x is, let's go with a half, that other solution we found earlier. So my left-hand side is going to be 20 times a half, take 35, that's minus 25. And then I'm going to lose my bracket for A, I'm going to lose my bracket for B. So I'm just going to get the brackets for C, which are going to be 0.5 plus 2. And then I've got 0.5 take 3. Which is minus 25 over 4. C, oh, I forgot to say that B was 1 in the first one, so I then have minus 25 divided by that gives me that C is positive 4. And we can then say, what's the last one we want? X is minus 2. Then the left-hand side is going to be 20 times minus 2 minus 35 is minus 75. I bet it's going to be 3. So I'm going to do the A bracket on this one because the other two have the x plus 2's in them. So I'm going to have, what's that going to be? Open brackets 2 minus 3. Whoops, I want minus 2 minus 3. Be careful not to make silly mistakes like this. Minus 2 minus 3. And then I'm going to have, what's that going to be? 2 times minus 2 minus 1, close brackets, 25. Look at that. Not quite right. It was minus 3, but I got 25a, so I got minus 75. Divided by the answer gives me that a is minus 3. So what that means then is if we go back to my integral, my differential equation, I'm at the stage where I've got integral 1 over y dy is actually equal to the integral of minus 3 over x plus 2 plus 1 over x minus 3 plus 4 over 2x minus 1 dx. Let's start working these out. So the left hand side is dead easy. 1 over y is just ln y. I'm going to have minus 3 lots of 1 over x plus 2 dx plus integral of 1 over x minus 3 dx plus 4 lots of 1 over 2x minus 1 dx. Now, the first two are very similar to each other. The third one is a little tiny bit more difficult, not a lot. So we can say something along the lines of, so for the first one, if we let u equal x plus 2, you could make it x plus minus 3 as well, you get the same result. Du by dx is 1. So you can just replace dx with du, and you have 1 over u, which you then put back. So you actually get, so ln y is minus 3 ln x plus 2 with modular symbols around there, just in case it becomes negative. Get the same on the next one, so you get plus ln x minus, oops, not close brackets, I want modulus. And then the last one's a smidge trickier because you've got that 2x in there. So on that one, let's just change my x's and so on. I've got 2x minus 1, so du by dx is 2, so dx is a half du, so I actually get plus 4 over 2 ln, and then I've got the modulus of 2x minus 1. It's a general solution, so I'm going to have a plus c on the end of this. So again, we are just going to have ln y is, let's combine these together, so I'm going to have minus ln of x plus 2 cubed plus ln of x minus 3 plus 4 over 2 is obviously 2, so I'm going to have ln 2x minus 1 squared. Bring all those in, I'm going to combine the powers. So y is going to be ln of x minus 3, 2x minus 1 squared over x plus 2 cubed, all modulus. Sorry, that should have been ln. I'm then going to raise both of these to the power e. There's a plus c on there on the end. Who cares what that is just yet? So y is going to be x minus 3, 2x minus 1 squared over x plus 2 cubed plus c. And that finishes off October 2020 OCR A-Level Paper 1.